Hello again everybody, and welcome to another how-to video here on John's Amazing Trains here on YouTube. Right now, quite a number of years ago I did a video on how to beef up the the Hornby is it 965 controller, which I'll come down here, which is this one here. Can't quite make out the number. What's it say? Yeah, I can't read it. 96. Oh, I was right, 965. Right, now the thing is, when I did that video, I'm using 3 of my conversions here, as you can see, for the 3 main lines on the layout, and they, like I say, they've all been converted. I've also done 2 more which run the lighting, and they've got cooling fans on the top, which is pulling the cold air up through the bottom and out the top. And the reason I've done that is because they control in the lights in 2 sections, because it's too much for one controller. And if I just come down here and just switch this on, right, you'll see that's just put all the lights on this part of the layout. And if I come down here and show you, you should be able to see that there, I can assure you it's reading 1.6, 1.7 amps. That's for that set of lights. So if I come back up here, right, knock those off like so, and then put that one on instead, that has now put all these lights on the left hand dog of the layout here, with all the station lights and everything. And again, if I come back down here, you'll see that that too is flicking between 1.6 and 1.7. So the 2 together obviously are going to be just about 3.4 amps. Let's just turn that back off. And in these I've had to change the rectifiers for 2 amp devices, because these only normally have 1 amp device, and we're going to be doing that again in a minute, because I've now in this video going to show you how to convert the later one, which is roughly 1995 onwards, when it was moved to China, and it's a completely different circuit, and it needs completely different outlook on how to do this. And so then here we are in the workshop on the bench with the later made in China one, which I must have had hundreds and hundreds of people asking me to do this, because obviously a lot of people have got this one, and the way I converted the earlier one, it's completely different. Like I said, you can't do the same thing with this. But after a collaboration with my friend John, who's brilliant with semiconductors and solid state stuff, we checked the circuit and everything out, and we decided that this is something like the right way to go, and it's actually much more simple than you'd think. Okay, before we actually go into this, I need to discuss a few things with you, because obviously many people out there, many people are not going to have any knowledge of this kind of thing. So as always with my how-to videos, I'm going to try and make it as simple as possible for you and try and explain everything. Right, if you look here, this is the transformer that you get. It's the plug with the transformer built in. This is what you get with the R965 controller. Now this transformer is exactly the same as the ones that's used on the earlier versions. So the transformer's the same, but the circuitry of this is completely different, and I'll try and explain it. First of all, you see here it says secondary 15 volt 5 VA. Now there's a formula here. If you divide the voltage into the VA, you get the current, and if you do that, it's 333.3 recurring milliamps. Now there's 1,000 milliamps in 1 amp, so we're roughly looking a third of an amp capability from this. And this is the important thing, because we're going to beef the controller up, but we also need to beef this up or change it for something different. So if you think about the 330 odd milliamps available from this transformer, it's in AC, which is alternating current. And again, like I say, both of them are alternating current. It's the same transformer for both controllers. Now the first controller that I did a few years ago worked on the principle that in the controller there's 4 diodes. And these are the 4 diodes, because they're in this one as well, and they're exactly the same as the other one. And these are 1 amp diodes. So you can see at 330 milliamps coming off here, the availability off there, they're quite comfortable at handling it because they're 1000 milliamps, and that, like I said, is the same as in the other controller. But this is where it changes. The DC in the other controller, which now is DC because, like I said, the diodes convert it to DC, which is direct current. That then is fed into a chip which is pulsed, controlled by a transistor. And basically what that means is the chip is pulsing the DC supply. Instead of being a solid straight DC, it's being switched like that. But it's still DC, not AC. So the DC, well, apparently, so I've read and heard over the years, a DC motor, like typically in all the model trains that we use, does actually like a pulsed DC. It's supposedly better for slow starting and slow running. But that's the difference between AC and DC. Now, one thing worth mentioning here, because even though you may not have any technical knowledge on this, it is possible that some of you have read or know that if you're on DCC, that the line voltage on the track is about 17 volts and it actually is AC, alternating current. But don't get put off by that, because it's very simple how it's done. The diodes, or the rectifier, or the bridge, what they call it, all different names for the component that converts AC into DC, alternating current into direct current, which the motor has to have to run, has to be DC. What they do, the 17 volts AC is on the track, but the rectifier is part of your decoder built in. So don't be confused by it, because the locomotive motor is still running on DC. Also at this point, it's important that I tell you that because we know we can get around about 1/3 of an amp off of this power supply, off the transformer, sorry. Well, it is a power supply, it's a transformer. These are underrun by about 1/3 because they're capable of 1000 milliamps, which is 1 amp. But we're going to beef this up, believe it or not, up to 4 amps, and that's a lot. Now, let me explain to you about the current that's required for locomotives. We can only give a rough guide because obviously they're all going to vary, and this is basically we don't want to take this into consideration when it's got a load on it, in other words pulling coaches. But basically speaking, a modern day locomotive roughly draws around 150 to 400 milliamps, which one of these is going to do. Absolutely, it will do it, because I say it's about 330 available. It'll go a bit more, obviously. Something like a Triang motor, the old stuff, they do kind of go around about the 400 milliamps and a bit more as well, which is why, I mean, this controller here, and along with the transformer, which you've seen, this and that actually only ever came with a view to run one locomotive around one track. It wasn't specifically designed for double and triple heading. It'll do a little bit more if you're using modern locos, you'll get 2 round with it, but you start doing 2 Triang motors and you're going to start struggling. So the plan is we're going to do this and we're going to beef it up to a good 4 amps. That's a massive improvement. And so before we get into this really quite simple upgrade, beef it up for this particular Chinese one, let me just try and explain to you briefly the difference between the two. Right, okay, the first one that I did, like I say, you've got the AC coming in, which is alternating current. The 4 diodes converted it to DC, which is direct current, and then there's a chip which then gets hold of that DC and pulsates it and feeds it into a transistor, which is the thing what we removed from the board and we put onto a heatsink because we were beefing it up. Now this works in a completely different way. If I just lift this device up, you'll see there it says Thyristor control, and this is like completely different. And the way this works is as easy as I can explain it to you. We get the AC input the same from the transformer in the plug socket. We have still got the 4 diodes which convert it to DC direct current, but it uses a part of the AC coming in to feed the circuit to create a pulse with this little device here, which then drives this thyristor here, which is why it's thyristor controlled. So if you were to feed it with DC, it won't work, whereas the other one would still work. And hence the three I'm using upstairs, and on the lighting I'm feeding that with a very expensive and very powerful stabilised pure DC supply. But you supply this with DC, it won't happen. It has to have an AC input. So that's, as best as I can explain it to you in English, that's the difference between the two. So we're going to go down the line now of giving this a massive upgrade. Okie dokie, let's get on with the job then. First of all, we're going to do what we did in the last one on the other video with the older version of the controller. We're going to remove this lead, which is scrawny, thin. This is the lead that goes to your track, which is the output from the unit here. It's very thin. It will quite easily carry about 500 milliamps, half an amp. So going back to the fact that we've only got around about 350 odd milliamps available to us, this piece of wire is going to be perfectly all right for its original intended purposes, feeding the track, running a single loco. But it's not beefy enough for what we want to do. So as before in the old video, sorry, we're going to use these auxiliary terminals, which are nice and hefty, for our output. So the first thing we do is get rid of this output lead. So I'll just flip that over, hopefully get the old iron on the go. Now I can't look at the camera at the same time, but I'm going to try and keep it in frame for you. Just basically it's these two on the pads here. There's one out and that's the other one out, so we can chuck that bit of junk scrawny wire in the bin. Right, what we need to do now is we need to separate these two output terminals. We're going to break the print here and here, which I did on the last one, so I'll do that and come back to you. Okay, that's done that then. Made a bit of a hash of it actually, because I've been trying to rush, I suppose, but you can clearly see I've broken the print there and I've broken the print there, which leaves these two isolated, which means we can use these for our nice beefy 4 amp outputs. And what we're going to simply do, again as I did in the last controller, is these were the two output pads where the two wires, the flimsy wire we've just taken off. We're going to put a couple of wires on here to there and from there to there, which is a bit more beefy to do the job. So I'll do that and back to you again. Okay, here you can see I've now, from our two original output pads which are here, which had the skinny flimsy cable on, I've now got a pair of nice hefty red and black 1.5mm cables, which will definitely carry 4 amps or more to our main output terminals here now, after having separated the print there and there as previously said. So we'll move on to the next part of the mod. Okay, next part it is. Now, I mentioned to you earlier we've got the 4 diodes here, and these are 100 volt capability, which is fine because we're only on about 15 volts or so, and they are capable of 1000 milliamps, 1 amp, but we want to go to 4000 milliamps, 4 amps. So these have obviously got to go. So what I'll do, I'll take one out. You could take them all out in one go because it's actually marked on the board which way round to put them, and the polarity is important. But I'll just take the one out to show you how I do it. I use this as a solder sucker and this as solder wick to get the last bit off the print. So again, I can't look at the camera while I'm doing it, but hopefully it'll be in the right position. I think I need to get some solder out this sucker. Hang on. Oh, stuck to it. Right, okay, here we go. Like I say, I'll just take one out, get it warmed up, and get that bit off. Try again. Yep, it's getting there. That's the first bit out. Get the solder out, and then the same again with this one, the other side of it, sorry. So here. Yeah, that's not too bad. So if I can get the last bit off with the solder wick. Yeah, it's getting there. That's all right. Yep. Ouch! It's getting warm as well, as it does. Yep, that's about there, I reckon. Yep. So if I can pull that out for you, I should be able to lift it up with the screwdriver. Yes. Come on, out you come. Come on, don't be stubborn. Yeah, we got it. Not quite on that one. Let's try it. Just warm it up a bit more. Got a little bit of lump on its leg, I think. Yeah, that's it. Okay, that's one of them out, and I will clean these pads off with the with this to get a nice clean hole before I put the replacement ones in. But that's how you take them out. And I will just again point out to you that you can see we've got a large block there on the board. There. So that's the. As you look at the diode, you can see clearly that it's got the line on it here. So that's obviously goes in that way, and like I say, these two are that way and these two are the opposite way, but it's very important you keep the polarity correct. But like I say, it's on the board, you can't get that wrong. So I'll take the rest of them out, I'll clean all the holes up with the desoldering braid, so we're ready to put the new ones in, and then I'll tell you all about them. Okay gang, like I said, here you can see I've removed all four of the diodes, and you can clearly see the markings there. We've got the two lines there on that end and the two lines there on that end for the bottom two, and if ever you are going to sort of get into this kind of thing and it's not something you've done in the past, then I strongly recommend that you do treat yourself to a desoldering pump like that, which is great for getting the first bit off, and then use some desoldering braid like this, because it works really good on the pads of PCBs, printed circuit boards, for getting it nice and clean like that, with all the holes exposed, ready for putting the new replacement components in. So that's next up to do. Okay, so let's now talk about the new diodes that we're going to put in, the slightly more beefier ones. This is one of them here. It's a BYV 27/150, I believe, and it comes in a pack of 10 like so. I've just taken this one out, obviously. Now these diodes, like the previous ones that were in it, which are the little black ones, okay, like that, the one there, they have a line on them, as you can see, the silver line we spoke about earlier, but in this case it's a black line, but that doesn't matter because it denotes which way is the correct polarity, and you just use the line as the way to put it in. Now these are these are 100 volts, exactly like the original ones, but these are 2000 milliamp, 2 amp. Now you may think to yourself, well hang on, we're supposed to be beefing this thing up to 4 amps. Well, we are. Let me explain. You can buy diodes anything up to the hundreds of amps, and obviously you can buy 3 and 4 amp ones, but when it goes up above 2 amps, which like I said these are, the legs become thicker. And yes, if I was doing this for myself, I would have actually bought 4 or 5 amp diodes, but the thicker legs would have meant that I would have had to drill the holes out. Now I don't have a problem doing that, I have the gear to do that, but because I know that people are going to be doing this and probably taking a risk at doing something they don't know anything about, it would mean having to have the drill and the correct drill sizes for the holes, etc. So I thought I'd do it this way. We can still get 4 amps from it, but we're going to do it this way by using the 2 amp diodes, and I'll show you how, so stay with me as always. And so here you can see I've placed the 4 diodes into the printed circuit board with the polarity correct. We've got the 2 black lines there, which is the thick markings on the board, and these 2 are the opposite way to make sure we've got the polarity correct. So let's just whip it over, and I haven't soldered them yet, so I'll do that right now, and then move on from there. Right, let me just solder these up. Right. Let's get a nice flow on there. That's beautiful. And the other one, the other side there, that's beautiful. So there's no point in me doing all of them on camera, but just go through and do them all, and I'll be back to you in a second or two. Okay, there we go. These are all soldered in now, as you can clearly see here. I've cut the legs off, but also, as you can see, I haven't cut them flush, not yet, and there's a reason for that. And what I'm going to do now is I'm going to get 4 more, because these come as a pack of 10 anyway. I'm going to get 4 more of the diodes. I'm going to double them up, but I'm going to do them underneath here on the board. I'm going to put them in parallel. Now, it is known in the electronics industry that paralleling diodes is not generally accepted. However, it does work, and it's very, very, very extremely rare that there is a problem in doing so by paralleling them. And that means, because these are 2 amp devices, we've changed the 1 amp ones to these now, which is 2 amp, but if we parallel with 4 more on here, on this side of the board, we've now got 4 amp capability. So come on, let's go for it. Okay, look, I've just done the one. You can see now why I didn't cut the legs off. So I basically put that one across the legs, soldered it into place, and then I've snipped the legs off both of these 2 here, and of course the 2 long legs that would be there. So I'll do the other 3, and just one thing worth pointing out to you before I do move on is this. Look, remember that you're going to be paralleling these, which means the polarity has to be the same on both this one and the one underneath. So in this case, look, this is the top one, or the bottom one in this case. It's got the black line here to my left. So when you turn the board over, make sure the black line is to the left, so that both diodes are exactly the same way. And this one's going to be same, but then these 2 will be the opposite way, exactly like it is on the top. Here we go then. All done. The 4 rated diodes here on the top in the original place as the original ones, and then 4 more parallels underneath the board. There's loads of room under here, so that's perfectly alright, and I've now cut all the loose ends off, and that now gives us a 4 amp capability to pull through this baby here. Okay, one more thing to go. Okie dokie, all that done and said is fine, but there is one final thing we need to do, and that is this. Now, if you have watched the previous one that I did a few years ago now, you'll remember that the transistor that was here, that was taking the load, had to be removed and replaced for a more hefty transistor, but at the same time it also had to be mounted on a heatsink to remove the heat away from it, because it was going to be doing more work. Now, the same thing does apply here, but there is something more simple about this. This thyristor, the model of this thyristor, is actually a 5 amp device. Yes, 5 amp, and we're only going to be looking 4 amp maximum, so this doesn't need to be changed because it'll do it. But the trouble is, it's mounted here just in the circuit board with no heatsink to conduct the heat away, and that's quite simply because with the power transformer, which we spoke about earlier, that's only capable of 300 or so milliamps, which is not, it's only 1/3 of an amp. And obviously this controller was originally intended to run, like I said earlier, again, a single locomotive, maybe double-headed if it's modern, running around a track, and it doesn't need much more than about 350 milliamps. And even though this is capable of 5,000, it's soldered into the board here with no heatsink, and which is actually called free air. In other words, it's mounted with free air, nothing to take the heat away. But at 300 milliamps or so, it's not going to get hot because it's capable of 5,000. So what we're going to do, as before, we're going to remove this from the board, and we're going to mount it on a heatsink with some fly leads back to the board, but we don't need to change it for a different device because it is capable, like I said, of 5 amps. So that is the next step to do. Okay then, out comes the thyristor. We'll start here. Same as I've said before, I can't look at the camera, so monitor, so hopefully you're going to see it. That one was a good one anyway. Just carefully get that flowing. Oops, not so good. Cockwood over. Try again. Come on, that's it. Warm it up. Got it. Yes, that's got it. I'll get the last bit off with the wick anyway. Come on, come on. Just one leg's holding it. Yep, can see it. Oops, you can't. Got it. Okay. Right, I'll just clean that off with the wick. like I've shown you before. Actually, I don't really need to, the holes are there, but I'll just give it a little bit off. Anyway, it does make a difference if you do this. Yeah, it just gets that big lumpy bit off. Yes. Okay, we're ready for the wires there. So the next step is just to point out to you, obviously that is the front of the thyristor. It's got the writing on it, as you can see there, and obviously that's the back. So when we put it back in, we've obviously got it marked on the board. Look, we've got cathode, anode and gate, which is K, A and G. So we'll put some wires on this and find a heatsink for it, and I'll be back with you in a few seconds. Right, here then I've prepared a bit of ribbon cable, which is 3 pieces to cut off a piece of 3. It's not essential that you use ribbon cable. You can just use 3 separate pieces of wire, it really doesn't matter. But I've just done this because it's the way I like to do it. So I'm just going to tin those up so it's flowing, nice and warm and nice and really flowing. So that's cool. I'm going to put some shrink-on sleeving on these. If you do use shrink-on sleeving, don't put it on till after you've tinned them, because the heat travels down the wire and it does actually start to shrink it quicker than you want it to. So I'll put the shrink-on now, and then we're going to put the 3 wires on the thyristor just here. Right, okay, I'm using my little man here to hold the thyristor for me. It's very convenient that, I call it my little man. Now, although the thyristor's have obviously been taken out of the circuit board and it's got some solder on the legs, I would highly recommend that you put some clean fresh solder on, as you can clearly see I have done there. So what we're going to do, I've also prepared those as well, look, and put the shrink-on sleeving on ready. And again, I'm going to try and do this, but I cannot look at the camera. Hopefully you're going to get it. So carefully does it. We got one on. Just let me slide that up there now. I'll shrink them all afterwards, obviously. Let's try and get that lined up. Come on. It's been a bit difficult to do. Alright, come on. Line it up, John. Line it up, John. Got it. Slide that one up now. That's it. And then finally the one on this end. It's very fiddly. Come on, line it up. It's being awkward. To bend that a bit. That's better. Got it. I hope you saw that all okay. Push this up. That's it. We can shrink them all on now. The shrink sleeving, the cigarette lighter, to shrink them. So we'll do that now. Where is it? It's here. Yep. Done. Perfect. Spot on. Right, on to the next bit. Right, the next thing we need to do is find a heatsink for our thyristor, because we need to keep it a bit cooler than just being in free air, like I mentioned earlier in the video. So heat sinks like this, they come in all different shapes and sizes. Figuratively speaking, the bigger the better. Good place to find them is an old power supply, like there, look, this one here. The best place is to find them if you've got any defunct or faulty computer power supplies. They've got them in. So again, but I will obviously at the end of the video and in the descriptions box, I will put a list of the items you need, which is not very much, that's for sure. I'll put the component values in, and I'll put a link to where you can get the parts you need, which is actually, it's only going to be the diodes, to be honest with you. That's the only thing I've bought is the diodes. The rest of it is just as is. So yeah, right, well, I'm going to use this heatsink, this particular one here, and the reason I'm going to use it is because it fits lovely and snugly into the case down there, look. So it's going to fit in there, and it's not going to interfere with the board. There's nothing on the board that's going to be that far down. If you see there, look, it's not going to be a problem from where I can see here. So I'll get that drilled, and I'll carry on with the video and show you how to fit it. Radio, as you can see there, I've drilled a hole in the top quite simply by using the heatsink as a template, like that. So we need to put all this together with Thyristor, but one thing we need to do first with the Thyristor is this. Right, on the back we need to put a little bit of heatsink compound. This messy stuff this is. Oh, you get it on your hands, it's hard work, horrible. So using a cocktail stick, the recommendation is about the size of a match head. So I'd say, yeah, it's probably a bit of an overkill still, but it doesn't matter, it's not going to really hurt anything. But you carefully put some of this on the back, which obviously you know that that's the back. There, let's get rid of that. Straight. Right, so carefully put that down a minute on its face. Right, let's see if we can put this together on the camera, hopefully. So, nice screw. Yep, that's the heatsink in place down there. Right, so now carefully, with the paste to the heatsink, of course, we're going to try and get that down there, which we have. Obviously it'll pull up tight in a minute. Right, and this is going to be fun, getting my fingers down for the nut, although there is a way I can do it, but hang on, it might be alright yet. Oh, come on, John. Come on. I think it started. Right, I'm not going to risk it, I'm going to use my nut spinner. Yeah, it was cross-threaded, I think. Oh, it's still not going on. What's up with this damn thing? Just tried it as well. Right, hang on guys, it's going on cross-threaded, I don't know why. I'll just stop the camera and I'll have a bash at it. Yeah, it's gone on there, it was being a pain in the ass. Right. Right, I think the camera keeps losing focus a bit when I get my hands in it. Right, just square it up, more or less, to be critical about this. Tighten it up, yeah. So there we go, Thyristor heatsink compound in place on a heatsink. Now, regardless of the heatsink you use, don't forget you can actually cut any of this plastic away here. The only reason it's got this big empty box section here is because the very first ones of these, the transformer, the plug-in bit in the wall, was actually in here as well. And why they've just started doing it as two separate items, I don't know. Probably some sort of safety thing in mind, but anyway, so that's the Thyristor in place with the heatsink and just quite simply bolted through the top like so. Yeah, and so now we need to put the wires here back in the board. Now I didn't measure anything here, I just deliberately put a long lead on because it doesn't matter, and it's easier to just manoeuvre it out the way when we put the base in back in the circuit board. Also worth pointing out to you, these three wires here, which we know are going to go in the board where the Thyristor was, I've actually very carefully but only slightly tinned the ends of those, just slightly flowing a bit of solder on the ends because it's easy to get them down the hole without them keep fraying out all the time. So we'll do that in a minute. Yeah, I think I'm going to have a cup of tea, but I've been in a few seconds for you. Well, I'm back. I did have a cup of tea, but I also ended up having about 3 hours of TV. So it's now late in the evening, about 10:20 here in the UK, and I'm now on the whiskey, but I'm still quite sober. Right, so let's carry on then. Whoops, don't knock the camera, John. Right, okay, we finished off with the Thyristor being bolted into place on the heatsink inside the case there. Now, looking at it, you know, because I've used a ribbon cable, the three wires will stay together. Like I said, you don't have to use ribbon, you could use three separate cables, it really doesn't matter, but obviously you've got to watch the polarity that you don't get it wrong. Well, we know that the Thyristor was in the board this way, so on the left is the black. So if we get the board now, just bring it into focus, hopefully. Right, what we need to do is, that's the way they're going to go in. So the black is on the left, which is the cathode. So we'll get that there. Now I can afford to bend that upwards. Let's just make sure it stays in while I do the job. Right, hold that. Right, we can afford to bend it upwards like that because it is in that direction where the part of the print is. So we'll just get that flat. Come on. Don't mess me about. Right, let's get that soldered. Let's do that first. Now I'm only going to do the one here to show you. Right, there you can see that I've only done the one, and I've bent it in the direction where it's not going to touch on anything else. I'll obviously snip that little bit off, but that's so I'll do the same with the other two. But of course you don't need to have that done on camera, so I'll do that and then come back to you. Here we go then, that's all three wires back in the print. We've got the cathode, the anode and the grid, obviously black, white, grey, and if we turn it over carefully, you'll see that I've done that, and basically I get it right, John. I bent that wire over in the direction of this part of the print, and that one into this part which is nothing, empty, and this one I bent down towards the bottom, and then I've soldered them and cut them off. And the reason I bent them over is that it's easier to just clean between them like that with a small screwdriver, just a little bit, and then have a close inspection of that section, because you can't afford for solder to have jumped across. It's so easily done, but you can't afford that for that to happen. They have to be completely insulated from each other, or isolated from each other. So just to recap briefly then, we've taken the old output cable off. We've broken the print there and there to allow us to use these two terminals for our main output, which is going to have a lot more current available at it. So a couple of hefty wires there to do that. We've taken the 1 amp diodes out, and we've put 2 amp diodes in on the top where the 1 amp ones were, but we've also doubled up by putting 4 more underneath, which gives us capability of 4 amps. Now I need to talk to you about the input socket here. On the other controller that I did a few years ago, I actually removed this and put a nice hefty pair of wires coming in, which you can do if you want, but you can also retain this if you want. It's a choice which is entirely yours. If you do take the socket off and solder wires on instead, then the wires go to that one and that one, or the other way around. The polarity doesn't matter at this point, and that one is just an anchorage point for the socket. So you just get the socket off and then solder your 2 wires onto that one and that one, either way round. But that's a choice of your own. Same thing applies with the heatsink and the fitting of it. You know, you could use different heat sinks. You can cut these out, like I said. You can. It's entirely up to you. There's no rule of thumb here how that's done. But one rule of thumb that is important is a saying that has been around for a long time. It's done now. I'm going to bend that over a little bit, look, that transistor, just so, I don't think it'll touch anything, but just be on the safe side, just bend it over a bit like that. Now look, there's a saying, the proof's in the pudding. So I tell you what, shall we prove it? Let's go and do that. Rightio then, let's show you around this, the way I've got everything set up for testing. First of all then, we've got 2 input supplies. We've got that one, which is here, which is the original power supply here, which is, we know, is capable of about 1/3 of an amp, around 330. We will go a bit more, but that's 330 or so milliamps. Next we've got this plug here, this one, which is a nice hefty 5 amp plug, which the leads I've soldered onto the connectors here from my Dinosaur battery charger. Just check that one out. She's old fashioned. I must have had that for donkey's years, but this is capable of more than 5 amps, about 5 amps actually. So we've got 2 massive differences in power supplies. We've got around 350 available to us off this one, and we've got around 5,000 available to us on that one. Now in doing so, I've not actually put the controller back in the case yet. We're going to leave it open until we've tested and proved everything. What I'm going to do, first one we're going to use, I've got here but basically a Dock shunt or an R159 double-ended diesels, R145 switcher, they're all the same. This is a fully reconditioned chassis that I use for checking the alignment of the wheels that I do when I sell the reprofiled wheels. And also, in line with that, we've also got the meter on so we can see how much current is actually being used. Now, I must tell you guys something about current, because a lot of people are certainly not going to understand this. So let me explain. When it comes to voltage, whether it be 12 volts or 240 volts, yes, you force the voltage into the item. The item could be just a model railway locomotive, or it could be a kettle in the kitchen. The voltage is always forced and present, but the current is not. The current is something that an item, again being a locomotive at 12 volts or a kettle at 240 volts, but the current is something that the item requires. Now, if the supply is not capable of supplying that amount of current that it is required, then that's where the problem starts. Hence the fact that the original power transformer, as we know here, for the simple Hornby single controller, it's only capable of giving or allowing around about 1/3 of an amp being pulled from it, whereas the battery charger there is capable of allowing 5,000 milliamps, which is 5 amps, to be pulled from it. So let's start with a test. Now, this test with this one chassis here, I'll explain to you. There's no wheels in this. It is just the motor, the bogie assembly. So let's think about this. First of all, there's no wheels in it, so it is only the motor that's turning. It will have a certain amount of restriction to turn, which will make it draw a certain amount of current, which is quite the normal. But bear this in mind, if the wheels were in it and the axles were in it, there would be more current required, because it would be trying to pull more current because of the slight drag of the cog on here and the wheels and the axle being in place. Not only that, if the wheels were on a track, you would have more drag. Now, each time there's more drag, the motor is going to pull more current. So if we add a load of coaches on as well, then what you're going to see on this test is not going to be anything like the real test, with wheels, axle in place, running on track and pulling a rake of coaches. So we're doing this quite blind in a way. So let's look. Right, okay, first of all, switch on the controller. Now, if you look at the meter, that's 50 milliamps, but the motor's not turning because it's not enough to turn it. So what we do is we turn up the control and the motor starts, and we'll keep going, gets faster and faster till we're right up full speed. And if we look at the meter now, typical Triang motor, it's drawing around 250 milliamps, which is cool, which is good, and that is perfectly all right for the original powered transformer, the wall plug one, because we know it's capable of around 330 milliamps. But remember, if this was running on a track with the axles in it and a load on it with coaches or wagons being pulled, that figure of 250 milliamps will be possibly double. Very close to double. Right, let's move on now with another test. Next here, I've added another powered bogie in. This time it's from the Heatsink, or maybe the Bud RDC, I'm not quite sure, the Bud diesel rail car. Anyway, the thing is, that's the second one, but again, I must stress the fact that there are no axles and wheels fitted in these, so the difference between having those in and then on a track and then pulling something will bring the required current that the motors will need, bring them up significantly, probably more than twice of what we're going to be seeing on this test. So remember, everything's switched off. So if I just come up to the meter again, get that right, as long as the light's not blasting into it. Okay, let's have a look. Yeah, that's cool. Right, I'm going to switch it on. We're in the down position. We've now got 50 milliamps, which is nothing really. That's because the motors have got current hitting them from the controller here, and they have got current, but it's not enough to turn them. But we'll turn the control up, and away we go. Right, that's 2 of them. We're still running on the original wall plug transformer, which is supposed to be give us an availability of around 330 milliamps. But if you look now at the meter, we're now up to 390, which is possibly just about its limit. And we can prove this as well. If I come back down here, right, and we'll just turn the controls back to 0. I'm going to unplug the original transformer here, there, and I'm now going to plug in our hefty 4000 milliamps supply, like so, and I'm now going to turn it back up to full speed again. Now look, that 390 milliamps has gone up to 430, which means just 2 Triang motors, early Triang or early Hornby, whichever, without axles and wheels, and without being on the track, and without pulling a weight behind them, they're already wanting 430 there. So that tells me that more or less, with the wheels, the track, and the amount of coaches and wagons you put on, we're going to be up to 1 amp there. Absolutely, we're going to be up to 1000 milliamps, which is straight away more, far more than the transformer can supply, the original one, and it's also more than the 1 amp diodes can supply. So yep, let's carry on. Right, this time we're now on 3 chassis. Again, no axles or wheels fitted. This time I've added in the EM2 class 37 Triang type chassis, and by the way, I do keep these in stock fully reconditioned because I do an exchange service on them as well. But anyway, so we've got 3 typical Triang motors there, 3 different ones, to do the tests again and see how the power supplies stand up to this. So first of all, we'll switch it on. Now we are back connected still to the original Triang Hornby power supply, the plug-in wall socket transformer, which, as we know and we've discussed a few times already, is capable of about 350 or so milliamps. And the moment you tick over without the motors running, we just join 50 again, which is pretty normal. So we'll come down here and we'll turn the speed up. Right, we're rolling. They're all 3 rolling. Yep. And we'll keep going up and up and up and up. Now we're at full power. Now I did notice that about the last half turn of the control didn't really seem to make much difference to the speed. And I do know the answer to that as why, because we've come up here, look. We're now drawing 570 milliamps off that 330 milliamp wall transformer, and as I'm sure you can possibly guess, if we kept this like this, it ain't going to last long, it's going to burn out. So we'll quickly come down here and stop it all. Cool. Central position. We'll remove the power supply, the Hornby one, which is now being drastically driven, well, not driven, but it's certainly being given a lot to do. We've now put in our big massive 4000 milliamp capability supply. So we'll go back to the motors again, switch them on, right, and immediately there's a difference. Now in 0 mode with the switch on the Hornby controller, we had 50 milliamps. We've now got 100, which is automatically showing us that 3 motors is too much for a Hornby controller, but certainly not too much for our battery charger, our car battery charger, at around 5000 milliamps capability. So come on, let's wind these up again. Here we go. And instantly I can hear them go faster when the control is turned right up, and that tells me they must be drawing more current than the transformer from Hornby's little wall plug supply can do. Let's have a look. Absolutely, look, 690 roughly milliamps. That is now way above the Hornby wall plug transformer can do, but it's certainly no problem to our 5,000 milliamp supply from a car battery charger. Even the Thyristor as it is. Wow! Now, I'm going to show you one more thing that's really going to blow your mind. Well, here we are then on the final big test, and let me show you what we're doing. Okay, first of all, we've got still got the dock shunter motor there, and we've got the high mech one there, and then we've got the EM2 there, or it could be the class 37, whichever, and then over there we've got one from a Blue Pullman and one from a class 101, and then up here we've got an X04 5-pole. So we've now got 6 motors on the go. So let's switch her on and let's see what happens with the original power supply. Right, here we go. That's struggling, one of them's not started. Yep, that's not running at high speed. None of these are running at high speed at all. One of them hasn't even started. And that was about, let's have a look. Yeah, 900 milliamps. So that's way over the top for our wall plug transformer. So now, let's do it again. Stay with me while I unplug that and put in our nice beefy hefty supply, like so. Right, same thing again, 6 motors. That's kicking them all up virtually instantly, and you'll hear the speed of them now. That's flat out, all of them. Every single one is running full tilt, absolutely no problem at all. And we look at the current now, and we're drawing 1.25 amps, or 1.24, it's going to flicker a little bit, so that's 1,240 milliamps. Now, if you are to load them, or load one of them, I'll show you if I can. I'm going to slow this one down with my fingers. See how more current's required? That's brought it down to about half speed. So you can see now what I mean. If when the wheels and axles are in, and it's on a track and pulling a rake of coaches, the current's going to be double, easily going to be double. So that's at 1,250, what we've got there. We can double that. Obviously that's going to be like 3 amps or thereabouts, and all the motors are going to vary. So there you go, chaps, that's it, all done. I know everybody's been waiting a long time for me to do this video, so I hope it's been worth the wait. So I think with that I'll say see you all, and get myself another cup of tea. Oh yeah, it's the next day now, by the way. So if I think of anything that I've forgotten to tell you or show you, I'll put it in the description box. But there you go, guys. See you. Bye.